Swayam Prabha. Digital India. Educated India.
Project. Okay. Let me get some preliminaries going. So, welcome to day 3, and today we'll look at the blast curve and basically some details on how to consider for design purposes on any, I call it structural, but you can apply it to any other structure as well, not necessarily structural. So, any questions before we get started? No? Okay. So, an idea of what we will cover today, we are making slight changes. So, things we'll look at is what is known as it the Friedlander? Friedlander, right? Yeah. I hope the spelling is correct. So, this is sort of the basis for a lot of things that we do in blast. The one you saw yesterday, the blast curves, the Friedlander curve and other equations. This is for blast loading. I'll give you some examples. I thought of maybe making a tutorial on it, but I think we can skip that. You can do it on your own time. And we'll focus on blast loading on, when I say walls on sides, on walls, roofs, roof, back, wall, and we'll look at two different, this is for types of loads, for blast loads due to explosion. You'll see we've made some comparisons, you'll see some differences, but a lot of similarities as well. Blast loads due to petrochemical blast. So this is, we use UFC 340-02, and this second one we will use a number of equations, and associated with it we'll go with the theory part of it. When I say theory, it is basically the procedures, how to use UFC 340, and then again these are equations, and we'll go through, and hopefully we'll have time to compare both. If not, we will proceed with either in the tutorial session or tomorrow. So, the main, you've seen yesterday the characteristics of the curve. So, let's say this is the Friedlander curve, and a typical blast load, it has a rise time. We saw that yesterday, that it has an arrival time. So, this is TA, and whether it is PR, and this is the time, or PSO, whichever you consider. So, if this is TA, and then there is a rise, and let's assume the rise time is it's often quite minimal. So, the line almost is straight, order of 1/10 or 1/100th of the total duration of the load itself. And then you have an exponential curve that goes something like this. And so, this is the arrival time, TA, and then you have from here to here, this is your TD plus the positive duration. So, here we have the arrival time, this is the positive duration, and here let us say this is the PSO value, this is, you can say, positive, and here this is the PSO value that is negative, and then you have here the TD negative. So this is the basic expression, the basic curve, and the most common expression that is used if you are doing any research in this, or if you want to explore this topic a little bit more, you'll probably go to this equation. Most of them use this expression because there are complexities even here, but it's a simple expression. I'll explain where the complexity is. So it is PSO multiplied by 1 minus, now let's say T prime is T minus TA. So the variable here is T prime, and divided by the duration T prime divided by TD, multiplied by, it's an exponential decay. So therefore minus B again T prime divided by TD. Now in what you see as a simple expression, as a simple curve in UFC 340. So I think we are having a little hard time getting the PDF file. So we'll upload this also. So if you look at the analytical equations, so make this a little bit zoom to fit width. Okay. So if you look at various analytical expressions, so this is the first one. We'll have the years also little late. You see, oh, it's right here. So Baker proposed the Friedlander and the modified Friedlander equation. So the modified is basically, this is the atmospheric pressure, and this is what I had written just now. If you see the decay coefficient is B, and it seems to be a very precise expression, right? In terms of all the uncertainties, it seems to go to even the 4th decimal, and that's how publications are there. Well, those days it was analytical expressions they were using. So you can see this is again the validity of Z from 0.1 to 10 meters per kg cubed. Now multiple people in those days, and this is something again I keep reminding myself that with advent of computers, if this had been there in 1950s, I don't think we would have had all these expressions to be shown. I don't know what they'll do 50 years down the road. But back in the 50s, his analysis and there were conditions, and again I do not know the background of the research itself, I'm just showing what is presented in the papers. So for the positive side on pressures, you see they had expressions, simpler expressions, but this is as in terms of Z, and again for two different ranges, if you see Z square and Z cubed, and these are all basically expansions of the exponential series, right? In math you would have done how to do a algebraic numerical expansion for different kinds of series, and this is basically what that is. So that was one in 55. Topic was revisited again in 1985 by two other researchers, and they proposed a much more complex expression, as you can see out here. Again, you can look up, if you were interested, what kind of tests they performed and what was the motivation to even change this expression, what was the deficiencies. Unless you're going to find deficiencies, you're not going to try something different, right? So you can look into that. And then couple of years down the road, went back to something similar to what Broad had written, but if you see the coefficients, they are quite different, and here there is a constant and they don't have a constant out here. So that was, and then, well, this is a little bit older as well. So these are some of the available expressions. And Kavi Arasu has done a really nice comparison. This was actually from last night. So, if you see the peak overpressure as a function of Z. I mean, this involves actually fairly complex calculations. If you see, I haven't shown you everything. There are ways to the equations to calculate the B values are a little different for many of them. So, you see the comparisons, and they are relatively, this is in a log scale, it is done from Z 0 to 10, and you see they sort of overlap each other with minor changes. And this is what you see in the UFC figure 2-7 and figure 2-50. So, that is a little background, and thanks to Kavi Arasu for putting this together. I think if you are interested, okay, let me put it this way, if you are interested further in knowing how some of these expressions are calculated, the decay coefficients, I have a page of equations on that, and you can come and I can either make a copy or you can let me know, I can send you a copy of that, because we will focus a little bit more on design. So, that covers. Any questions on this topic? I think you had something else, right? Let me see, there was one more. Yeah, there's one more curve. Which equation did you use here?
The same example that you just showed.
Oh, the same example that I had. Okay. So, you see for this was developed for two different, for R is 13, but different W values. So, the Z values, the pressure time curves, if you see it goes in this particular. The other was a spectrum as a function of Z, right. So, this is if you take for a given Z value and a given W and R, of course, you can see how the curves are quite. This is a pressure time curve, that was the function of pressure versus Z curve. So, what are we considering today? Blast loading on walls, and again all types of walls. The main types are front, side, roof and back wall. So, just to give a picture of what a schematic for reference purposes, keep this in mind. Remember, you can have buildings of different footprints. So, we will take a simple example with footprints that are rectangular and with a height, common height. So, this is the width of the wall B, and the blast loading is in this manner. And so, this is your height of the building, and this is your length of the building. And as we have seen yesterday, here is where you have the blast load itself. The blast wave propagates from here on in this manner. The tail, sort of the reverse of the Friedlander equation. Once the peak comes, it starts decaying, and that's your standoff distance. This is W and this is R. Couple of things we noted yesterday was on this face you have PSO. Again, PSO is basically P incident. These are all used terms that are used interchangeably, PSO or PI. So if you see me writing that, that's because I've seen it in both forms. So that's your side on, and then you also have a reflected pressure. So on these walls you only have PSO, here you have PSO, and on the back wall also it's in the opposite to. So for structural purposes, if you are considering, so this is, let's say, side wall, this is roof, this is PSO on the back wall. For structural purposes, if you are considering just like you would do for wind has additive leeward and windward components. Similarly, you can do an analysis based on these pressures. And in practical applications, you could, what we have done, we've tried this with bridges. We've used a standard bridge design software, and those are all static loads, but we have converted these loads into pressures in this manner and applied, and of course it is much higher, as some kind of a static load. You could add factors. I mean, I don't know if there's a whole lot of research, like you have an impact factor in bridges due to dynamic loads. Those kinds of, I don't know if there are impact factors. So those are some things that you'll have to account for. So what we will calculate with this is equivalent triangular loads. So we'll start with and I'll superpose the equivalent part. The Friedlander equation, if you see, the curve would look something like this, and going with PSO, let's say this is PSO and this is the time. So we also have, this is PSO plus, here we have PSO minus. The equivalent triangle, this is, if you see, we are breaking this into equivalent triangular loads. So equivalence is based on the impulse. So this is the impulse equivalence is considered. Basically, the impulse under the Friedlander curve is the same as the impulse under the triangular loads. So if we, let's say, look at that, the positive, this is the positive impulse, the positive phase. And if you consider the positive impulse, you can take the impulse, some of it comes off, some of it comes in. So the blue part would be the equivalent impulse in this case. So the blue and the green areas are equal. So this is TOF. And this is your T naught or TD, the duration of the positive phase. Then you also have, this is TO minus, and this is broken down into, so now you have the negative impulse also. So the negative impulse is broken down into two triangles. One, so this is considered to be 0.25 TOF minus, and the rest of it is out there. So that's quarter of it, and so the TOF is basically, let's say the positive phase impulse is IS plus. So, TOF is 2 IS plus divided by the pressure is maintained. So, what you see out here is the peak pressure does not change, and then the impulses are equated. Same thing with the negative impulse part of it. So, TOF minus is 2 IS negative divided by PSO negative. So, here PSO negative, this whole thing is IS negative. Any questions? Now, when you look at the front face loading, so that's the basic principle, but let's go one by one, and these are from the UFC. I was planning to draw it, but then I decided last evening that it's better to take some snapshots. It'll be easier to demonstrate. Again, let me know if you're not able to see the figures clearly. We are trying to make it a little wider. That's fine, right? Okay. So they might use slightly different, or the front wall loading. They're using slightly different terminology, but it's the same thing. The front wall loading. So shock direct, this is the width, this is the height, and remember this, the length is right here. So here we are not in front wall is PR. We really don't design for PSO. So the front wall designed, and as I mentioned, this is showing a simple box, can be applied to any type of structure that you are using, even moving vehicles, as long as you know that at that you make it a quasi freeze it in time, and then if you are looking at some of those, what kind of pressures, if you are designing vehicles for this type of loading, you can use these numbers there as well. At least you have a good estimate of, if not accurate, definitely estimate. Going a little tangent, do you know the difference between precise and accurate? Okay, I mean, all great perspectives. There could be no right answer, but what am I drawing? And have you seen these boards where you throw darts, dart board, right? And you do a dart board and you hit. In one case, this is person 1, another case person 2. Who's precise, who's accurate? Wait, put it this way, yeah. Person 2 is? Yeah, this is, so now this is precise, right? He's very close on the line, but it's not really accurate. So this is accurate. So although it is spread all over, this is more, I don't know, just thought of it. So as an illustration for the difference between the two of them. So coming back to the context of it, you might be precise to some extent, but whether you're accurate, it's a judgment call. So this is PR. Now they notice there are a couple of other things. There is also in the front face, there is your PSO and you also have the blast wind pressure. We also call this the dynamic pressure. And recollect that we had discussed a coefficient of drag. The wind, there is always a drag associated with it. So, if CD is the coefficient of drag, so what we see out here is in the front wall, the pressure versus time curve. So, this is PR versus PR is the peak value, but in general the pressure versus the time curve. It has various components. The first thing, it hits PR comes, and remember the triangularization. So, we triangularize it and you can actually extend this down. So, this blue line, you can extend it down, and then you also have, this is what is known as stagnation pressure. Essentially, when the reflected comes down to what is around ambient, put it this way. So, that is what is known as the stagnation pressure. So, that is nothing but a side on plus your coefficient of drag multiplied by the dynamic pressure that is associated with it. The coefficient of drag is taken to be 0.1 for front wall, then you have minus 0.4 for all other walls, because here it is directly impacting in the front. So, its positive is considered into the surface. On the other side, since it is flowing around and the PSO is acting towards, the drag is taking away some of the pressures that are acting. Now, so that is a blue line. If you see, this is the red line. So, the drag also, they have the equation, and you will see the TOF that we calculated. So, the drag stagnation pressure goes to 0 over the load TOF. It is not the load duration, but it is TOF. The load duration is more here. Now, the point where the pressure PR reduces to the curve that represents the stagnation pressure. The stagnation pressure, that is the peak value on the left side, this blue one, and that goes to 0 till here. Now, this is the point which is called the clearing time. So, TC is the clearing time, basically the time required for the pressure, or the reflected pressure I should say, to decrease to the ambient pressure. It is not, or the ambient air pressure at that time. And then the curve actually that you will use for design purposes is this curve. For calculating, this would be your design curve. We will see, this is your reflected impulse that we talked about. The TRF, here they call it TRF, that is the equivalent time for for the loading will, and here if you see this is the positive phase. The negative phase, it starts with T naught, and T naught is, remember the Friedlander curve will actually follow and go through T naught and come up. So now sort of we are taking the Friedlander curve out of our imagination, but when you see T naught, that's what T naught represents. Now, so from T naught to T RF minus, and T RF minus will go through the calculation there. So here if you see, this is 0.25 T RF minus, so this is up to a quarter point and then it decreases down. So any questions on this part? So that's the front wall loading, and we'll definitely go through an example. So the clearing time Tc is given as, now these are for explosions. Petrochemical facilities we'll talk about later. You do get something similar. We'll do have a comparison. So if you ever work in that, or you can see there are some easier equations to use. The reason I'd like to present both is using these UFC expressions or the procedures for petrochemical facilities may not be, maybe overestimating, or they are not applicable so much for the lower pressures that you experience. So this is given as 4S divided by 1 plus R multiplied by a reflection coefficient Cr. Lot more terms that are being introduced. So this S is the lesser of the minimum of either the width by 2. So let me redraw the picture of the building. Maybe it's not. So this is the height and this is the width. So the lesser of W by 2 or H, the height, then R is given as S over G, where G is the larger of W by 2 or H, and Cr is the speed of sound. This image, this is from figure 2-192 in the UFC 340, and it's actually a function of PSO. And as I've already mentioned, CD equal to 1.0 for front walls, comes from 2-153 of UFC 340. So let me drop, I think I have those, some of them. So paste out here. I think you can see this, right? You can, I think I might be going over the page. So I'll just try to leave it at that. Oh. What happened? No. Maybe it is there in the background, you think? So let me save this so that we don't lose that. Let me try one more time pasting it. Anyway, you can refer to figure 1-2-192. So this is figure, and I'll show that. So basically here you have CR, and this, if you see, is PSO in PSI. So let me show this so you can see here, and it goes from the incident overpressures goes from 0 to 75, and these values go from 1 to 1.1 to 2, and the units, I believe, could be feet per millisecond, right? Have a look at that. I believe that would be the case. So CR goes from, ranges are from 1 to 2, and this is going from 0 to 75 psi. And I don't know if I have 153, let me check that. I don't think I have that, but you can check figure 2-153, and that's where you'll see CD is equal to 1.0 for front walls. Then we look at next roof and side walls. Roof and side walls, the procedures are similar. There is slight difference in how you would like to interpret. I'll talk about that. But roof and side walls, some basics before I bring in a picture. This pressure uses the incident pressure or the side-on pressure. That's why in the case of buildings they call side-on, because from the sides on it is applied, but under normal circumstances you would call it PI. This value, as we have seen, is reduced by the negative drag pressure. The drag coefficient CD is a negative value. It depends on this calculation is, in other words, since we are looking at, and let me at this point discuss both of them. So if you are looking at the side wall, so this is your LW. Same thing here, LW. Now side wall, as you know that you will have a certain PSO1 here. At this point you will have a certain PSO, let's say PSOF. I'm just giving PSOF and PSOB. Why? Standoff difference is, and it can be quite a large drop, but that's your choice what you want to design it for. So you were asking me about masonry walls, right? So if you have a column, for example, so this is, let's say, a column, and then there's another column, and in between you have a masonry wall. You can calculate your, let's say this is L1, this is, let's say, L1 prime. So depending, you probably will design your columns for one pressure. You're not going to design each column differently. You might take the worst. So if you're designing a column, for example, or if it is just a full wall, this is your choice. L1 is typically 1 feet, the first 1 feet, because you'll see later there is a coefficient that depends on the choice of L1. So if you're designing the wall, you might start the side-on pressure here, PSO, let's say W, and then you might say, okay, I'll consider L1 prime to be equal to, again, subjective, is the length of the wall. What you're doing there is you are averaging. By consider longer L1, it averages across the wall. Now if you ask me, will there be damage in the front part of the wall? That again depends. So I might design it for 1 feet front part of the wall and go all the way through. So this way I have extra, it's not, since you're going through the process, the cost is taken care of in some way. So be conservative to some extent. But if you want to go average, that's fine and completely your choice. When you come to the roof, it's exactly the same thing. Now in the roof, let's say you have steel joists or concrete beams, whatever it is. You might say in the roof, that particular beam is taking tributary area over this part. So you probably will calculate PSO here and then use this as L1. So choices again, if you're designing the slab, you could perhaps take the first part of it and then design the slab for that particular load. So these are some minor differences. So technically, you can say it is a step-by-step procedure for different locations on the wall and the roof. But the loading curve is a little different. So if it is P versus T, now let's say this is roof. Depending on where you are, let's say this is TF and there is an increase rise time and then there is a drop time, and then it continues. Maybe I think I may have a picture, I'll use that. The same thing, you have the negative phases and the positive phases for this. The negative phase starts with T0, keep that in mind. This is the duration of the positive phase. That you originally calculate. This TF, this would be the TD plus TF, and here you have TF plus. So this is your rise time and P. So let me see if I have a picture of that. Yeah. Copy and so for reference, this is from figure 2 190, 2195. So what you see here is PR, TF, TF plus TD, and this curve is what PS plus CD times Q. That's the peak value. So here you have P roof or the P side wall is there is a coefficient CE multiplied by plus the drag coefficient multiplied by the drag is associated with the wind pressure. And the negative phase, you have your arrival time TF plus TO. This is your arrival time, depending on where you consider. If you're considering the back part of the wall, the TF arrival time could be the same as the front part of the wall if it is the first foot of the wall. And what you have here again is TF arrival time, T naught is the positive phase duration. So TF arrival time. I know can be a little confusing, we've used TD, TA and things like that. TF plus T naught plus 0.25, and then this is the negative phase, and then here you have PR minus. The drag coefficient is little more for petrochemical facilities. You have just one numbers, but the drag coefficient CD for 0 to 25 psi, again can convert to kilopascal, roughly 1 psi is how much? 7, right? Yeah. Seven kilopascals. So the drag coefficient CD for 0 to 25 psi is minus 0.4. For 25 to 30, most of your Q naught is going to be fairly low. So quite often you will just be in the first range. And 50 to 130 psi. So this is 25 to 50, 50 to 130 psi. So as the pressure increases, it actually drops down. So the curve is similar for both front wall and the side walls. I'm sorry, the side walls and the roof. So we have here roof and side walls. Then for now comes the last one, rear wall. Now in the rear wall, it's similar, only thing now you have the arrival time. Here it is PSO, let's say rear wall, and this is the time. Same thing you have now, a triangular loading and again a triangular loading here. So here you have, maybe we can pull down the picture so that it will be easier to be consistent. Okay, let me, I forgot to mention this. In the previous one, I used a coefficient CE. That coefficient is, let me insert it here. So, CE is what is known as the equivalent load factor, and it's a function of the wavelength to the span length that you consider. So, CE is an equivalent load factor. Basically, what is it doing? It is giving a coefficient for you. Again, it goes from 0 to 1. It's giving you a coefficient that you attach to the PSOF. CD we have seen. Let me put here itself, equivalent load factor. And so that equivalent load factor, this is for peak equivalent uniform roof pressures. Positive pressure, so you have a CE positive and a CE negative. And here, if you see, this is a function of LW divided by L1, wavelength by span length. Because the speed of sound, LW is nothing but U multiplied by TD, speed of the wave multiplied by TD. So, depends on how deep it is in terms of the U times TD, the wavelength, blast wavelength, and the span length. So, it does decrease over time. So, that is a factor. As you see that if the span length and this is in a numerical sense, your span length will never approach your wavelength. So, often you might be fairly low, let us say even if you go 0.5, those factors you are looking at in the ranges of somewhere 0.3 to 0.35. You will never be going into the very high ranges. I had another set of notes. So, I will probably present this one and then we can take a break and then we will come back with doing the problem, right, for this. That might be a good segue. So, any questions at this point so far? Okay, something like wind you are talking about, right? In wind, for example, you have suction pressures. Yeah. Yeah. That's not considered here. That's not considered here. So, you get into fully ventilated versus non-ventilated systems. I don't think I have seen that being considered or significant enough to be considered for design purposes.
So that will be more than I think outside pressure?
Not necessarily in this case. In the case of wind, yes. If you see wind loading, you could have as much as 20% of the external pressures. So, it becomes a significant value and it adds to it. Whereas, if you see in blast, I don't think it will reach anything up to even 5 or 10% what is inside. And even if it is there, how do you quantify it, right? You need some kind of, again, tests or whatever it is to say, okay, it is at 10% rather than just a wild guess.
Especially the back wall, the pressure which is reaching there, PSO, it will be lower.
Much lower, yes.
Lower than what maybe the internal pressure on the back wall.
It could be. It could be. But then you're not transmitting directly unless there is an opening. That pressure doesn't get transmitted. The pressure is already absorbed by the front wall, and then anything else behind gets transmitted. So by the time that goes through, I think those pressures are going to be fairly low, and that's why they're not considered here.
So do we assume that these are fully ventilated?
So those ventilation things come into play only if you have internal explosions. So I will take up an example also, a simple example of internal explosion where those ventilation factors come into play. And the curves for determining the pressures due to internal, because there is a lot of reflection and then there is the interaction between both those curves are very different from the curves that we see out here. But for outside explosions, those ventilation factors are not quite considered.
Again, also this CE value
Uh-huh.
depends upon LW.
Yeah, wavelength.
Oh, wavelength.
Yeah. LW, if you see here, wavelength divided by the span length.
So wavelength is not that duration of the total duration TD, positive TD plus minus negative duration.
No, the wavelength is, so the blast wavelength, if you recollect the definition, it was L multiplied by your U multiplied by TD. So it depends on how long in terms of length does the wave that the blast lasts. So there is a blast speed.
Is it the pulse width of the wave blast?
No, it's not the, okay, that's a good point you raise, and it's not like a sinusoidal curve as I had mentioned earlier. So it is not the wavelength that you see from a sinusoidal curve, or the frequency, well, the frequency is different, but here is TD over which it lasts. Then you have the speed. So knowing the speed, knowing the length, knowing TD, multiply the two, you get the length over which you can expect that blast wave to last. It's a very good point, so keep that distinction in mind. Is that clear to everybody? Okay.
So the material influence is there. Does it also form a parameter because the way it propagates?
With the material of?
It could be a masonry wall, it could be an RC wall, it could be.
Okay. No, the design is based on, so the load calculations are independent of what the structure to be designed.
But for the propagation, there could be some sort of
There
dissipation depending upon the.
Yeah, there could be. Again, those are some things, engineering judgment. What do you account for? Is it significant enough? If it is significant enough, that's a first judgment, then you account for it in design.
Okay, so the material type is not a parameter.
Yeah. That comes in the other four aspects that we talked about yesterday. Yeah. Yeah, I think let me pull this all set. I had shown this is roof and side wall. We covered the rear wall also. Let me put that in here. So for the rear wall, the main difference here is so you see here the shock front is going, and this is your typical something like wind, the pressures that are acting, but the wall loads are considered in the following manner. Here the peak value is CE plus the PS on the back wall. So PSO back wall, that's what it represents. So drag coefficient, and then you also have CE minus PSO. So you are recalculate PSO for the back wall. You can use the same PSO for the side wall and front. The same PSO that you calculate for the front wall, you can use for the side wall and roof. For the back wall, you can use a different one. Then that's the curve going down. So you have TB, the rise time, TD, and TB plus TOF. So this is your TOF, and this is your TOF minus, and then it starts at T naught. T naught is the positive load duration. I think that's the last one I had, so I can close this. Now for petrochemical facilities, you tend to have lower pressures. You still have the side on, you also have the reflected pressures, drag, all those still exist. So equations are an easier way and perhaps more accurate also. We will do a comparison for you to see, to calculate the parameters. What are the primary equations that we use? The first one is PR is CR multiplied by PSO, and some of the coefficients that we see out here can be used because we don't have the earlier precursor document. If you have the book for petrochemical facilities, some of those curves are mentioned. Going back to the history of 340, what the three segments of the armed forces did, the Navy had their own documents, Army had their own documents. The Army document was TM 1500, and then the Air Force had their own. So they combined all of them into a UFC 340-02. So some of these they use from the Army documents because that's more applicable. So coefficients can be used from appropriate coefficients as you see. Again, a lot of it is judgment call, which is the right one you choose. So the CR is from there. Then the second equation is for, and that's what you see here, PSO less than or equal to 20 psi. If it goes beyond that, then you're not quite on your own, but you're using value judgment there. So CR is given as 2 plus 0.05 PSO, that's PSO, and this is in PSI. So remember, when you use PR, there is a CR multiplied by a PSO. This is in PSI. If you're using in, this is 2 plus 0.073 PA or in kPa. And keep in mind, CR is dependent on the angle of incidence. And there is another curve for that. We have seen yesterday, I've shown you some curves related to that. Then the third equation is the dynamic or the blast wind pressure, and this expression is given as Q naught, which is 2.5 PSO square by 7 P naught plus PSO, or in a simpler form, P naught is the atmospheric pressure. This is 0.022 PSO square in PSI, or 0.0032 PSO square in. So for Q naught, I'd use these expressions. Then the next quantity is the P naught, let me mention that, is the ambient air pressure. Then the next quantity, okay, I did mention this, but let me mention this one more time, that the net dynamic wind pressure is, we have seen this earlier also, is CD multiplied by Q naught. Then fourth, the shock front velocity also has a simpler expression. So U is 1130 multiplied by 1 plus 0.058 PSO multiplied by half, getting in feet per second, or 345 1 plus 0.0083 PSO power half in meters per second. Here we assume that the pressure wave travels at the same speed as the shock wave. So you calculate the shock velocity, and then the question that has been raised just now is the blast wavelength. It's not exactly, I think the confusion comes because we are calling it a wavelength. So you might think of it, maybe separate this words in this manner. So maybe that's helpful to understand the difference between a wavelength versus blast wave. Maybe put this as one word and blast wave length. So that'll be easier to remember. But it's a really great question. And that's perfectly the natural thing to do. Even I thought when I was looking at the first time, okay, wavelength, where is a wavelength? I questioned for a while, I don't see a wavelength that is repeating in any manner, and then I recognized that it is the distance over which you can expect the blast wave. Maybe we can write that down. A couple of weeks down the road you'll forget. Distance over which the blast wave has an impact, has an effect. And which is why if you see the length of the building, of course you won't have blast wavelengths can be fairly high in the hundreds of feet per second. If you have a building that is 100 feet, then the whole effect tends to come down if you are averaging basically. So, this is U multiplied by the TD. Then another thing that might help you to understand is the pressure trails off to ambient pressure over LW. And here loading, it's similar, it's a little bit easier. We don't consider negative effects in negative phase, not considered in petrochemical design, structure design. So, you still have the P versus T. So, you have PR over T effective, and then you also have the clearance time. So, so this is the T effective, that is just a line I am drawing, but you have here the Q naught, or maybe let me take this out. So, you have here then the Q naught comes, and this value here is PS, the stagnation pressure. This is the clearance time. The stagnation pressure for these is given as PS is the peak value of the stagnation pressure is the same, PSO plus CD multiplied by Q naught, and the positive impulse, as you can see, is 1/2. If you take PR minus PS and you consider this part of it, so PR minus PS is this part of it, so 1/2 PR minus PS multiplied by TC, plus then the bottom part of it is here is 1/2 PS multiplied by TD, and TC is given as, it is a different expression, 3S divided by U less than TD, and U is this, as we have seen before, the wave speed, and S is the minimum of H or height or B by 2, the width divided by 2. Then we can go a little over, no? Finish this part. Okay. Then the sidewall loading or the roof is again similar. You have here now, but now you have 2 times. You have T1 and T2, and this is PA. So the equations corresponding to the side walls are PA is CE multiplied by PSO plus CD multiplied by Q naught. And you can, as I've seen, CE from either the UFC 340, you can take that. And then you have T1 is equal to L divided by U, and T2, this is the rise time, and T2 is T1 plus TD. So there is a graph for CE versus the L over LW. From here the graph looks something like this. It actually goes, and you can calculate it from that. And then finally, the roof wall, not roof, the back wall, rear wall. So the rear wall load similar now the arrival time, this is L over U. This is basically the length of the side wall divided by the wave speed. So this is your time here, and this distance, rise time, is S over U, and S is the minimum, as we've talked about. Where was it? Somewhere here. S is the minimum of H, or the B by 2, and then this one is TD. And the peak value P, let's say back wall PB, is CE PSO plus CD Q naught. So you see there is a pattern. So looks like that's the end of the page. So we'll stop with that for, and then when we come back, we'll take up problems in both. Yeah.
Can we have this L, length of the side wall, or for that matter distance of the back wall? Can it be greater than the wavelength of the black?
Yeah, if it is, yeah, it can be, but the effects, then CE starts going down extensively. So the graph that you see here, right, your CE values, if your L is much, I think it's the other, LW by L maybe, I might have reversed length, wavelength. So what you're saying is, if the value is very low, that factor comes from here.
But by definition we say that blast effects
Yeah,
like
ignored. So you can say, you can justify in your design saying that it is beyond that, so you're ignoring it. Yeah.
or is there any minimum pressure that we have to design?
Not that I know of. There's no, then you design it for wind pressures. Minimum is the wind pressures. Wind pressures go what, 30 psf, or 30 by 150 is roughly 0.3 psi, 3 by 15, right, 1/5 basically, 0.2 psi, 0.3 psi, so you're down in that range. How do you consider that? Is that what your question is? So okay, good question. Again, all the standoffs, it comes from the PSO. So you calculate your PSO from those curves, and we've seen how to calculate those Freelander curves. So if you are automating a procedure, developing your own programs to do that, that's why I wanted to present those equations in case you want to automate some process. You can use those equations with a good confidence. Otherwise, you can use the charts, calculate your PSO. We've seen some of it yesterday, so you go through that particular process. All right, we're now getting into the nitty-gritty details of